Imagine looking out into the night sky and discovering that almost everything you can see, the stars, the galaxies, the glowing clouds of gas, is only a tiny fraction of what the universe actually contains. Not 10%, not even 5%. Everything humanity has ever observed directly makes up only about 5% of the total cosmic budget. The remaining 95% is invisible. Most people have heard of dark matter. It is mysterious enough on its own. But dark matter is not the greatest mystery in modern physics. That title belongs to something even stranger: dark energy. Unlike dark matter, which helps gravity pull galaxies together, dark energy appears to do exactly the opposite. It drives the expansion of the universe faster and faster with every passing second. And yet, no telescope has ever seen it. No camera has ever photographed it. No laboratory has ever isolated a single particle of it. We cannot touch it, capture it, or even point to a place in space and say, there it is. Everything scientists know about dark energy comes from observing what it does, not what it is. Imagine walking into a room where no one is present, yet books begin sliding across the shelves by themselves. You never see the person responsible, but every movement tells you that something unseen is influencing the room. That is our relationship with dark energy. We never observe it directly.
We only witness the universe behaving as though something invisible is pushing everything apart. If this mysterious force did not exist, our current understanding of the cosmos would fall apart. Entire theories about the history and future of the universe would no longer make sense. Perhaps the most astonishing part is that physicists still do not know what dark energy actually is. Not because they have not looked hard enough, but because nature itself may have hidden it in a way that prevents us from ever seeing it directly. Today, we're going to explore one of the deepest mysteries in science. We'll begin with something deceptively simple. What does it actually mean for the universe to expand? Most people imagine the universe as a gigantic empty container filled with galaxies, stars, planets, and black holes. If the universe expands, they imagine those galaxies flying through empty space, like shrapnel from an explosion. That picture is completely wrong. The universe is not expanding into anything. Space itself is expanding. This idea sounds almost impossible to picture because our brains evolved to understand ordinary motion. We understand a car driving down a road. We understand an airplane moving through the sky. Every movement we experience happens inside space. But according to modern cosmology, the large-scale expansion of the universe is different. The space between distant galaxies is increasing. The galaxies are not racing through a fixed cosmic arena. Instead, the arena itself is stretching. This distinction changes everything. To understand why, we have to travel back over a century. In the early 20th century, most scientists believed the universe was static. Even after developing his theory of general relativity in 1915, Albert Einstein assumed the universe neither expanded nor contracted. His own equations, however, disagreed with it. General relativity describes gravity not as a force pulling objects across empty space, but as the curvature of spacetime itself. Matter and energy tell spacetime how to curve, while curved spacetime tells matter how to move. When Einstein solved his equations for the entire universe, they predicted something unexpected. A universe filled with matter could not remain perfectly still. Gravity would cause it either to collapse inward or expand outward. Since astronomers at the time believed the universe was static, Einstein introduced an additional mathematical term into his equations. He called it the cosmological constant. Its purpose was simple. It acted as a kind of cosmic repulsion that exactly balanced gravity, allowing the universe to remain motionless. For years, this seemed like a clever mathematical adjustment, But then, observations transformed everything. In the 1920s, American astronomer Edwin Hubble carefully measured distant galaxies using observations from the Hooker telescope at Mount Wilson Observatory. He found something remarkable. Nearly every distant galaxy appeared to be moving away from us. Even stranger, the farther away a galaxy was, the faster it appeared to recede. This relationship became known as Hubble's law. At first glance, this might suggest Earth occupies the center of the universe, but that interpretation is completely false. Imagine dots drawn on the surface of an inflating balloon. As the balloon expands, every dot sees every other dot moving away. No matter which dot you stand on, the universe appears to expand in all directions. There is no unique center on the balloon's surface. Likewise, our three-dimensional universe does not require a central location from which everything expands. Every galaxy observes roughly the same large-scale expansion. This was one of the first profound clues that space itself changes over time. The universe was not eternal and unchanging. It had a dynamic history. As astronomers collected better observations over the following decades, another extraordinary realization emerged. If galaxies are moving farther apart today, then billions of years ago, they must have been much closer together. Continue rewinding the cosmic movie, and eventually all galaxies occupy an unimaginably small, hot, and dense state. This became the foundation of what we now call the Big Bang model. Contrary to popular belief, the Big Bang was not an explosion occurring at one point in space. It was the rapid expansion of space itself from an extremely hot and dense early state. Every region of today's observable universe was once compressed into conditions so extreme that ordinary atoms could not even exist. The first few 100,000 years after the Big Bang were unlike anything we experience today. Temperatures exceeded thousands, and earlier billions of degrees. Matter existed as an intensely energetic plasma of electrons, protons, atomic nuclei, and photons continuously scattering from one another. Light itself could not travel freely. The universe was effectively opaque. Only after approximately 380,000 years did temperatures fall enough for electrons to combine with nuclei, forming the first neutral atoms. Suddenly, light could move across space almost unhindered. That ancient light still exists today. After traveling for nearly 13.8 billion years, it reaches Earth as the cosmic microwave background, a faint glow discovered accidentally in 1965 by Arno Penzias and Robert Wilson. This relic radiation provides one of the strongest pieces of evidence supporting the Big Bang model. It also serves as a snapshot of the infant universe with extraordinary precision. When satellites such as COBE, WMAP, and later Planck mapped this ancient light, they revealed tiny temperature differences of only a few millionths of a degree. Those minuscule fluctuations became the seeds from which every galaxy, every star, every planet, and eventually every living creature would form. Everything we know, including ourselves, originated from those almost unimaginably small imperfections. At this point, cosmologists believed they had assembled a remarkably successful picture of the universe. Gravity slowly gathered matter into galaxies. Galaxies clustered into enormous cosmic webs stretching across hundreds of millions of light years. The universe expanded because of the Big Bang, but gravity should gradually slow that expansion over time. It seemed almost unavoidable. After all, gravity is always attractive. Every galaxy pulls on every other galaxy. Even across billions of light years, gravity never truly switches off. The only remaining question appeared to be how much the expansion had slowed since the Big Bang. No one expected the answer that observations would soon reveal. And that answer would force scientists to resurrect the very mathematical idea Einstein once introduced and later regretted. By the early 1990s, cosmologists were no longer asking whether the universe was expanding. That question had already been settled decades earlier. Instead, they were trying to answer something much more precise. How quickly is gravity slowing the expansion? The expectation seemed almost obvious. Imagine throwing a ball upward from Earth's surface. The ball rises rapidly at first, but gravity continuously steals a little of its speed. Unless it escapes Earth's gravitational pull entirely, it eventually slows, stops, and falls back. Many physicists expected the universe to behave in a similar way. The Big Bang had given space an enormous initial expansion. Gravity, generated by every star, every galaxy, every cloud of gas, and especially every concentration of dark matter, should gradually reduce that speed. The only uncertainty was the rate. Would gravity eventually stop the expansion altogether? Would the universe collapse in a big crunch? Or would expansion continue forever, becoming slower and slower? For decades, these possibilities dominated cosmology. Then came one of the greatest scientific surprises of the 20th century. Instead of measuring galaxies directly, astronomers searched for something that could serve as a reliable cosmic distance marker. They needed an object whose true brightness was already known. If you know how bright a light bulb actually is, then simply measuring how dim it appears tells you how far away it must be. Astronomers call such objects standard candles. Among the best standard candles are Type Ia supernovae. These extraordinary stellar explosions occur under very specific circumstances. A white dwarf, the dense remnant left behind after a sun-like star dies, can orbit a companion star. As it steals material from its partner, its mass slowly increases. If it approaches approximately 1.4 times the mass of the Sun, known as the Chandrasekhar limit, after physicist Subramanian Chandrasekhar, the pressure supporting the white dwarf can no longer remain stable. A runaway thermonuclear reaction ignites throughout the star in just seconds. The entire white dwarf is destroyed. Because these explosions occur at nearly the same critical mass, their peak brightness is remarkably consistent. That makes them powerful measuring tools across billions of light years. In the late 1990s, two independent research teams set out to measure how the expansion of the universe had changed over cosmic time. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees playing a central role in analyzing the observations. Neither team expected to rewrite cosmology. They expected to measure how much gravity had slowed the expansion over. Instead, they found something impossible. The distant supernova appeared dimmer than predicted. At first, this looked like bad news. Perhaps interstellar dust was absorbing the light. Maybe the supernova themselves had evolved over billions of years. Perhaps there were hidden observational errors. Scientists are trained to distrust extraordinary conclusions until every ordinary explanation has been eliminated. So both teams spent years checking every possible source of error. Again and again, the same answer emerged. The supernova were farther away than expected. The universe had expanded more than gravity alone allowed. There was only one conclusion left. The expansion of the universe was not slowing down. It was speeding up. This announcement, published independently in 1998, completely overturned decades of expectation. It is difficult to overstate how shocking this result was. Imagine throwing a ball upward. You watch it rise. Instead of slowing under gravity, it begins accelerating away from Earth all by itself. Every law of everyday experience tells you that cannot happen. Yet, on the largest scales imaginable, the universe appeared to behave exactly this way. Something was overcoming gravity. Something invisible filled the cosmos. Something was steadily causing distant galaxies to separate faster and faster as billions of years passed. That unknown influence became known as dark energy. The name itself can be misleading. Dark energy is not simply ordinary energy hidden in darkness. The word dark means unknown. Just as dark matter is called dark because it neither emits nor absorbs detectable light, dark energy earns its name because its physical nature remains unidentified. In fact, unlike dark matter, dark energy may not even consist of particles. That single possibility already separates it from almost everything familiar in physics. Nearly everything around us is made of particles. Electrons, protons, neutrons, neutrinos, photons. Even the recently discovered Higgs boson is a particle. An excitation of the Higgs field predicted decades before its detection at CERN in 2012. Modern particle physics, described by the Standard Model, explains nature using quantum fields spread throughout spacetime.
Particles are localized excitations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Wherever you go in the universe, these fields already exist. Particles are simply tiny disturbances moving through them. Dark energy, however, refuses to fit comfortably into this picture. No experiment has detected a dark energy particle. No detector has measured a stream of dark energy radiation. No collision inside the Large Hadron Collider has revealed a new particle carrying the required properties. Instead, dark energy behaves less like an object and more like a property of space itself. This distinction is profound. When we think of empty space, we instinctively imagine nothing. No atoms, no dust, no planets, no stars, just emptiness. Modern physics paints an entirely different picture. Even the emptiest region of intergalactic space is not truly empty. It contains quantum fields extending everywhere. According to quantum field theory, these fields can never become perfectly motionless. Even at absolute zero temperature, where all ordinary thermal motion disappears, quantum uncertainty remains. This consequence arises from one of the central principles of quantum mechanics, the Heisenberg uncertainty principle. Although it is often introduced using position and momentum, uncertainty also applies to energy and time in a subtle way. Very briefly, quantum systems can fluctuate. Tiny amounts of energy can momentarily appear and disappear without violating the fundamental mathematics of quantum theory. These fluctuations are often described as virtual particle pairs continually emerging from and returning to the quantum vacuum. It is important to emphasize that this popular picture is a simplified visualization rather than a literal swarm of particles popping into existence. In modern quantum field theory, vacuum fluctuations are properties of the underlying fields themselves, not miniature particles constantly flying around. Nevertheless, the analogy captures an essential truth. What we call empty space possesses measurable physical activity. This idea is not merely philosophical. One of its most striking experimental confirmations is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and later measured with increasing precision. Place two extremely smooth metal plates only a tiny fraction of a millimeter apart in a vacuum. Quantum fluctuations between the plates differ slightly from those outside them. That imbalance creates an extremely small but measurable force pushing the plates together. The Casimir effect demonstrates that the quantum vacuum is not empty in the classical sense. It has structure. It possesses energy. This realization immediately raises an astonishing possibility. What if dark energy is simply the energy of empty space itself? Remarkably,
Einstein's cosmological constant can be interpreted exactly this way. Instead of representing an arbitrary mathematical correction, the cosmological constant may correspond to the intrinsic energy density of spacetime.
If empty space naturally contains energy, then as the universe expands and creates more space, that vacuum energy remains present everywhere. Unlike ordinary matter, whose density decreases as the universe expands because the same particles occupy an ever-increasing volume, vacuum energy maintains approximately the same density per unit volume. This difference changes everything. Imagine filling a gigantic warehouse with identical boxes. If you continually enlarge the warehouse while never adding more boxes, the average number of boxes per cubic meter steadily decreases. That is how matter behaves during cosmic expansion. Now imagine that every time the warehouse grows, new boxes somehow appear everywhere so that the average density never changes. Vacuum energy behaves mathematically in a similar way. As space expands, there is simply more space containing the same vacuum energy density. Consequently, the total amount associated with vacuum energy increases as the universe grows larger. This sounds almost like creating energy from nothing. Yet, within general relativity, the expanding universe does not obey the simple conservation law familiar from everyday mechanics. In dynamic spacetime, defining a single globally conserved energy for the entire universe is generally impossible. The geometry of spacetime itself evolves, and energy conservation must be understood locally through Einstein's field equations, rather than as a fixed cosmic total.
If dark energy is truly the energy of empty space, then an even deeper question immediately appears. How can empty space possess energy at all? For centuries, philosophers argued over whether empty space was even something that could exist. Ancient Greek thinkers, such as Aristotle, believed that a true vacuum was impossible. Nature, he argued, would always fill any empty region. The famous phrase, "nature abhors a vacuum," survived for nearly 2,000 years. But modern physics eventually reached an astonishingly different conclusion. The vacuum does exist, yet it is anything but empty. To understand why, we have to abandon one of the oldest pictures of reality. Imagine standing in a perfectly silent room. Your ears detect nothing. But that does not mean the room contains no air molecules. The molecules are still there, constantly moving. Their average behavior simply produces silence from your perspective. Quantum fields behave in a somewhat analogous way. Even when every detectable particle has been removed, the underlying fields remain. In quantum field theory, fields, not particles, are the most fundamental ingredients of nature. This idea represents one of the greatest conceptual revolutions in physics. For most of history, scientists viewed particles as the basic building blocks of reality.
Today, many physicists instead view particles as temporary excitations of fields that permeate all of spacetime. The electron field exists everywhere. The photon field exists everywhere. The quark fields exist everywhere. The Higgs field exists everywhere. Even the emptiest region between distant galaxy clusters is immersed in these invisible fields. This is not speculation. The Higgs field was confirmed experimentally in 2012 when the Higgs boson was detected at CERN's Large Hadron Collider, providing dramatic support for the field-based description developed within the Standard Model. Fields are therefore not mathematical conveniences. They appear to be genuine features of reality. But fields introduce an unavoidable consequence. According to quantum mechanics, they cannot remain perfectly still.
Werner Heisenberg's uncertainty principle tells us that certain pairs of physical quantities cannot simultaneously possess exact values. One consequence is that a field cannot have both a perfectly defined value and a perfectly defined rate of change everywhere. Complete stillness is forbidden. Even the vacuum contains irreducible fluctuations. Physicists call the lowest possible energy state of a quantum field its vacuum state. Ironically, the lowest possible energy is not zero. It still contains what is called zero-point energy. Every quantum field contributes a tiny amount.
Mass and energy tell spacetime how to curve. Spacetime tells matter how to move. Quantum mechanics, on the other hand, describes reality in terms of probabilities, wave functions, operators, and quantum fields. Individually, both theories have survived every experimental test ever performed within their respective domains. General relativity accurately predicts planetary orbits, black holes, gravitational lensing, gravitational waves, and the expansion of the universe. Quantum mechanics successfully explains atomic spectra, semiconductor electronics, lasers, nuclear reactions, superconductivity, and countless laboratory experiments to astonishing precision. Yet, when physicists attempt to combine these two frameworks under the extreme conditions of the early universe or inside black holes, profound mathematical inconsistencies appear. Dark energy may be one of the first visible signs that this union remains incomplete. It is almost as though the universe is quietly pointing toward a deeper theory that humanity has not yet discovered. Another fascinating aspect of dark energy is that it appears astonishingly uniform. Matter is clumpy. Stars gather into galaxies. Galaxies gather into clusters. Clusters connect through immense filaments, forming what astronomers call the cosmic web. On the largest observable scales, hundreds of billions of galaxies create an intricate network stretching across billions of light years. Between these filaments lie enormous cosmic voids, regions containing remarkably few galaxies. Some of these voids span more than 300 million light years. If you could travel through one, the night sky would appear dramatically emptier than it does from Earth. Gravity naturally amplifies these structures. Regions that begin slightly denser attract more matter. As they become denser, their gravity grows stronger, attracting even more material. This process, known as gravitational instability, transformed tiny fluctuations seen in the cosmic microwave background into the vast cosmic architecture observed today. Dark energy behaves in the opposite manner. It does not gather into clusters. It does not appear concentrated around galaxies. It does not seem stronger inside galaxy clusters than inside cosmic voids. Instead, every observation suggests that dark energy is almost perfectly smooth across the observable universe. Whether you stand inside the Virgo cluster or in one of the emptiest cosmic voids ever discovered, the density of dark energy appears nearly identical. This remarkable uniformity distinguishes it sharply from every familiar form of matter. Even dark matter, although invisible, forms enormous gravitational halos surrounding galaxies and clusters. Dark energy does not. It seems indifferent to cosmic structure. Imagine pouring water into a landscape. The water naturally flows into valleys. Matter behaves similarly, collecting wherever gravity is strongest. Dark energy resembles something entirely different. It fills every valley and every mountain with almost exactly the same density, refusing to collect anywhere in particular.
This uniformity becomes increasingly important as the universe grows older. Early in cosmic history, matter dominated the dynamics of expansion. Galaxies were much closer together. Gravity exerted a stronger influence because matter was packed into a smaller volume. As billions of years passed, cosmic expansion diluted the average density of matter. Dark energy, however,
hardly changed. Eventually, there came a time, roughly 5 billion years ago, when dark energy began to dominate the large-scale evolution of the universe. That moment marked one of the greatest transitions in cosmic history. For billions of years, gravity had been winning. Then, gradually, dark energy became the dominant influence. Today, according to the best measurements from the Planck satellite, combined with observations of supernovae and baryon acoustic oscillations, ordinary matter contributes only about 5% of the universe's total energy content, dark matter about 27%, and dark energy approximately 68%. In other words, nearly 7/10 of everything governing the evolution of the observable universe is something whose fundamental nature remains unknown. That realization is extraordinary. Human civilization has mapped the genomes of living organisms. We've landed spacecraft on distant planets. We have photographed the shadow of a black hole.
We have detected ripples in space-time produced by colliding black holes billions of light years away. Yet the dominant ingredient of the cosmos remains unidentified. Perhaps the most humbling lesson of dark energy is not simply that we lack answers. It is that the universe can behave according to precise mathematical laws while still hiding the underlying reason those laws exist. References discussed in this section: Weinberg, S., 1989, The Cosmological Constant Problem. Carroll, S.M., 2001, The Cosmological Constant. At this point, a natural question emerges. If dark energy fills all of space, why don't we notice it here on Earth? Why isn't our solar system expanding? Why aren't atoms, planets, or even galaxies being torn apart? The answer lies in one of the most beautiful aspects of physics. Different forces dominate at different scales. Imagine placing a tiny magnet on your desk. The magnet effortlessly lifts a steel paperclip against the entire gravitational pull of Earth. Gravity is acting on every atom in that paperclip, yet a much stronger electromagnetic force easily overcomes it. The universe works in much the same way. On the scale of atoms, the electromagnetic force binds electrons to atomic nuclei. The strong nuclear force binds protons and neutrons together inside the nucleus itself. These interactions are enormously stronger than the effect associated with cosmic expansion. On the scale of planets and stars, gravity dominates. The sun's gravity keeps Earth in orbit, and Earth's gravity keeps the moon bound to our planet. These systems are held together so tightly that the incredibly gentle stretching of space-time caused by dark energy is effectively negligible. Even entire galaxies remain gravitationally bound. The Milky Way, together with the Andromeda Galaxy and dozens of smaller companions, forms what astronomers call the local group. Despite the expansion of the universe, the Milky Way and Andromeda are actually moving toward one another and are expected to merge in roughly 4 to 5 billion years. Their mutual gravitational attraction is far stronger than the influence of dark energy across the relatively small distance separating them. Only when we look beyond galaxy groups, across tens or hundreds of millions of light years, does the accumulated effect of dark energy become dominant. At those immense distances, galaxies are no longer bound together strongly enough for gravity to overcome the expansion of space. This distinction is essential because it reveals that dark energy is not a force that pushes galaxies through space in the ordinary sense. Instead, it changes the large-scale evolution of space-time itself. Einstein's general relativity tells us that the geometry of space-time determines how matter moves, and dark energy appears to alter that geometry on the largest possible scales. One way to visualize this is to imagine drawing a grid on a rubber sheet. Place coins on the sheet to represent galaxies. If you slowly stretch the rubber, the coins move farther apart, even though they are not sliding across the surface. Their increasing separation comes from the stretching of the sheet itself. While this analogy has limitations, our universe is not literally a two-dimensional sheet. It captures an important idea.
The expansion belongs to space, not to the galaxies moving through a fixed background. This raises another profound question. Has dark energy always behaved in exactly the same way? The simplest cosmological model assumes that it has. In this picture, dark energy is equivalent to Einstein's cosmological constant, represented by the Greek letter lambda. Its energy density remains constant as the universe expands, making the standard cosmological model, often called the lambda CDM model, remarkably successful at explaining observations ranging from the cosmic microwave background to the large-scale distribution of galaxies.
Yet science advances by questioning even its most successful models. Some physicists have proposed that dark energy may not be constant at all. Instead, it could arise from a slowly evolving quantum field permeating the universe. One of the best-known ideas is called quintessence, introduced in the late 1990s. Unlike a cosmological constant, quintessence changes over time. If this picture is correct, the acceleration of the universe today may differ slightly from its acceleration billions of years ago. Other ideas are even more radical. Perhaps general relativity itself requires modification on cosmological scales. Einstein's theory has passed every experimental test within the solar system and has successfully predicted phenomena such as gravitational waves and black holes. But the observable universe spans more than 90 billion light-years, and it remains possible that gravity behaves differently across such unimaginable distances. A number of alternative theories, including modified gravity models such as F of R gravity and brane world scenarios, attempt to reproduce the observed acceleration without invoking dark energy as a separate physical component. So far, however, none has matched the overall success and simplicity of the standard lambda CDM model. That is why new observations are so important. Over the coming years, missions such as the Euclid Space Telescope, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope will map billions of galaxies with unprecedented precision. By measuring how galaxies cluster and how cosmic expansion has changed over time, astronomers hope to determine whether dark energy truly behaves like a cosmological constant, or whether subtle deviations point toward entirely new physics. Whatever the outcome, the implications reach far beyond cosmology. If dark energy is vacuum energy, it may reveal something fundamental about quantum fields that we have not yet understood.
If it is a new field, it would represent a previously unknown component of nature. If it signals a breakdown of general relativity on cosmic scales, then one of the greatest theories in science would require extension. In every case, dark energy is not an isolated mystery. It sits at the crossroads of quantum mechanics, gravitation, particle physics, and cosmology. That is why so many physicists consider it one of the most important unanswered questions in all of science. There is a certain humility in this realization. Every night, we look at a sky filled with stars and galaxies, believing we are seeing the universe itself. Yet those magnificent structures are only the visible islands in a much larger cosmic ocean. The motions of galaxies, the evolution of the cosmic web, and the fate of the universe all point toward an unseen ingredient that neither reflects light nor reveals its true identity. Perhaps one day, a new theory will unite quantum mechanics and gravity, explaining why empty space possesses the properties it does. Perhaps future telescopes will detect subtle signatures that distinguish vacuum energy from a dynamical field.
Or perhaps the answer will require a conceptual leap as revolutionary as Einstein's realization that gravity is the curvature of spacetime. History suggests that the deepest mysteries often become the gateways to entirely new ways of understanding reality. A century ago, the expansion of the universe was unimaginable. A few decades later, black holes were considered mathematical curiosities. Today, they are observed directly. Gravitational waves were once thought too small to detect. Now, they are measured routinely.
dark energy may one day follow the same path, from mystery to understanding. Until then, it stands as a reminder that science is not merely a collection of answers. It is a process of continually refining our picture of reality as new evidence appears. The fact that we cannot yet see dark energy directly does not diminish its importance. On the contrary, it highlights how much of the universe remains to be discovered. And perhaps the most remarkable thought of all is this: the greatest influence on the evolution of the cosmos is something we have never observed with our own eyes. We know it only through its imprint on galaxies, on space-time, and on the history of the universe itself. In learning to read those cosmic clues, humanity has already uncovered one of nature's deepest secrets, even if the final answer still lies beyond the horizon of our current understanding.